We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live, streaming in real time around the globe of them watching all of this. Take a look at this.
An interstellar visitor, unlike any before, is fast approaching our solar system, puzzling scientists worldwide with its bizarre behavior and improbable trajectory. What if an object zooming near Earth isn't just a random rock from deep space, but something far more mysterious? An intentional arrival demanding our attention. NASA and major observatories have dropped everything to study 3I Atlas, an object defying physics, chemistry, and even basic expectations of cometary behavior. With the world's best telescopes trained on it, could this be the first sign of something deliberately making contact with humanity at a moment we're uniquely prepared to observe? Detection and early discoveries. 3I Atlas emerged as a remarkable celestial visitor, first detected by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, in Hawaii. This system scans the skies rigorously, analyzing around 40,000 images nightly to identify objects moving against the fixed background of stars. What made 3I Atlas stand out was not just its movement, but its unexpected activity at distances far from the Sun, something that no typical comet or asteroid would exhibit. Yet, despite being caught on camera months earlier by NASA's test mission, the significance of this object wasn't immediately recognized. The delayed realization underscores a key limitation in how we currently search for interstellar visitors. Pattern recognition software is trained to identify objects that behave predictably, based on known solar system bodies. 3I Atlas did not follow these routines. It was bright and active when it should have been dormant, displaying colors and motions that defied the established norms. Its unusual journey made it effectively hide in plain sight, passing through the data unnoticed until astronomers pieced together the clues much later. Scientists liken this to a security camera accidentally filming a crime, but only discovering the footage after the culprits have announced their presence. This analogy highlights the serendipity and gaps inherent in our observation methods, and how critical timely analysis is for catching objects with novel behaviors. The very fact that 3I Atlas escaped immediate classification challenges us to rethink how we scan the cosmos for unexpected phenomena. As it came into focus, astronomers worldwide scrambled to confirm the object's trajectory and properties. It was found roughly 400 million miles from Earth, moving at speeds and angles that widened the scope of what was considered possible for interstellar travelers. The global astronomical community quickly recognized the need for intense monitoring, redirecting valuable observation time from other projects to this enigmatic visitor. This shift speaks volumes about the importance and rarity of catching a third interstellar object in real time, following just two others known to date. The rarity of such events magnifies the urgency and potential significance of what 3I Atlas might reveal. It also raises questions about whether similar objects might have passed undetected before, slipping through the observational net due to their unconventional properties. From the start, this object challenged conventional wisdom about where and how cometary activity begins. Typically, solar radiation ignites activity only when objects draw closer to the Sun, yet 3I/Atlas was already active even when far beyond Jupiter's orbit. This anomaly hinted at unusual internal chemistry or heat sources, sparking debates among astronomers about what materials or processes might be driving it. The combination of delayed discovery and early unexpected brightness framed 3I Atlas as a puzzle piece that does not fit traditional cosmic narratives. Its appearance urged the scientific community to expand the parameters within which interstellar visitors are sought and understood. The question moved beyond how it was found to why its behavior was so unlike anything else we've observed. This early phase of detection and recognition set the stage for deeper analyses into the object's composition and physical properties, which soon revealed even more striking surprises about its origins and nature. Unnatural chemistry. Once 3I-ATLAS's presence was established, spectral analysis became a priority to decode its chemical fingerprint, revealing a startling story about its origins. Astronomers broke down the light from its glowing coma into thousands of wavelengths, each corresponding to specific elements or molecules. What emerged was a chemical profile that defied the norms observed in our solar system. One of the most significant findings was the unusually high ratio of carbon dioxide to water, approximately 16:1. This ratio is far different from comets and bodies formed in oxygen-rich environments like ours and points to a cosmic birthplace where carbon compounds dominated rather than oxygen. A chemical environment suggests formation in regions around young stars or stars with evolutionary paths unlike our suns, perhaps billions of years ago in distant and inaccessible parts of the galaxy. But the real conundrum came with the metals detected. Nickel was present in measurable quantities, but iron, its nuclear sibling produced alongside nickel in stellar nucleosynthesis, was nowhere to be found. Under normal stellar evolution, these two elements are inseparable. Finding nickel without iron challenges fundamental understanding of how elements are synthesized and dispersed in space. Natural processes might explain this decoupling, but only under highly specific and very rare conditions. Perhaps the material comprising 3I/ATLAS experienced a unique form of chemical separation or processing before formation, or it arose from an exotic type of star or explosion we have yet to fully comprehend. Some scientists cautiously consider the possibility that artificial processes might explain these discrepancies, although such ideas remain controversial and speculative. Adding to the mystery, the dust particles around 3I-ATLAS show polarization signatures unlike anything seen previously. This pattern implies the dust grains have highly ordered internal structures that would be extremely difficult to form naturally in space. This engineered quality raises profound questions about whether the object's components could be artificially designed or modified. The tools used for these measurements are extraordinary, capable of identifying elemental concentrations as low as 1 part per million, enabling astronomers to detect even trace differences that convey significant clues about the object's origin. Such precision elevates the chemical puzzle to a level that demands serious reconsideration of prevailing cosmic formation theories. Taken together, these unnatural chemical and material signatures paint a picture of an object from an alien environment, possibly shaped by processes alien to the solar system, and perhaps even beyond current human understanding of natural formation. With chemical mysteries deepening, attention turned to the physical behaviors of 3I-ATLAS to see how they aligned or failed to align with accepted cometary physics. Breaking physics 3I-ATLAS outright defies one of the cornerstone rules governing comet behavior, the inverse square law of solar heating. Normally, comets brighten predictably as they approach the sun, their ices sublimating in known quantities based on solar radiation intensity. However, 3I-ATLAS was already active and bright at distances far exceeding those where such activity should begin, a flagrant violation of expected physics. This early activation suggests that either the object has materials that sublime at much lower temperatures than typical cosmic ices, or that it generates internal heat independent of the sun. Radioactive decay inside the object or other unknown sources might supply this heat, but confirming any such mechanisms would rewrite the textbooks on comet physics. Beyond its brightness, the object's luminosity varies in erratic bursts rather than smooth curves predicted by existing models. It behaves like a dimmer switch, flicking unpredictably between low and full brightness with no clear triggers. This behavior contrasts directly with established observations where comet brightness trends follow smooth, predictable patterns. Attempts to model 3I-ATLAS using conventional cometary physics repeatedly fall short, explaining some but not all phenomena before fundamentally breaking down. This mismatch suggests that the object's internal and surface processes are driven by physics or materials not previously observed or understood. It's as if the object plays by an entirely different set of cosmic rules. Consequently, astronomers have described the challenge of interpreting 3I-ATLAS's behaviors as trying to understand a game of poker using chess strategies. Some patterns seem familiar, but the overall context is entirely foreign. This analogy captures the frustration and curiosity inspired by the object's complex behaviors. 3I-ATLAS's ability to maintain and vary brightness inconsistently demands a reconsideration of comet activation and energy dissipation processes. Researchers are exploring hypotheses from exotic ices to radioactive heating, but none yet provide a fully satisfying explanation. The divergence from normal physics involved in both its brightness and activity patterns bolsters the notion that 3I-ATLAS originates from conditions or processes radically different from those shaping typical solar system comets. This insight enhances interest in how its trajectory and composition fit into the broader cosmic puzzle. Understanding these physical anomalies is crucial before moving further to examine the surprising path 3I-ATLAS takes through our solar system. Now that the object's unusual physics are clear, let's explore the orbital mechanics that make its trajectory so confounding. Orbital mechanics oddities. One of the most compelling mysteries of 3I-ATLAS lies in its trajectory through our solar system, which deviates sharply from the erratic paths typical of interstellar objects. Most visitors from beyond tend to enter on hyperbolic orbits with steep inclinations, traversing the solar system at high velocity along unpredictable routes. In contrast, 3I-ATLAS follows a path closely aligned with the ecliptic plane, the flat disk where most planets orbit, which strikes experts as extraordinary and statistically improbable. Researchers have calculated that the odds of an interstellar object arriving on such a precisely aligned trajectory are roughly 1 in several million. While not entirely impossible, such odds are so small that many scientists have stopped seeing this as mere coincidence. Instead, some now speculate that the trajectory might reflect deliberate positioning or guidance, adding a layer of intentionality to this cosmic visitor's arrival. The precision of orbital calculations involved in tracing 3I-ATLAS's path is remarkable. Advanced numerical integration techniques model gravitational interactions not just with the Sun, but with all significant solar system bodies, including planets, moons, and sizable asteroids, to achieve positional accuracy down to a few kilometers over years. This painstaking modeling confirms that the object's motions are far too exact to be random, sampling regions of space with a finesse unseen in typical stellar interlopers. 3I-ATLAS's orbit weaves it past Mars at a vantage point ideal for observation, then loops close to the Sun at perihelion, followed by planned encounters near Venus and Jupiter. Each approach is perfectly situated to maximize scientific observation opportunities while minimizing risks such as gravitational disruption or thermal destruction. It's a trajectory that reads like a carefully choreographed cosmic ballet rather than a chance orbital path. Such an efficiently tailored route is rare among natural objects, whose trajectories often swing too close to the Sun, disintegrating, or remain too distant to study meaningfully. Critics might argue this alignment is fortuitous, but the pattern's precision continues to puzzle orbital dynamics experts and fuels ongoing debate regarding its origin. The timing of 3I-ATLAS's arrival carried its own unusual significance. It coincides with a historic era when humans possess unprecedented observational capabilities, yet still face challenges interpreting such rare phenomena. Had this object appeared decades earlier, it likely would have gone unexamined in detail. Decades later, it might receive more scrutiny, but could coincide with shifting scientific priorities. The present timing equips humanity to notice and focus like never before. This rare convergence of trajectory, timing, and spacecraft availability has catalyzed an intense global satellite and telescope mobilization. In the weeks and months ahead, astronomers will track 3 IATLAS's passage with unparalleled precision, unlocking clues hidden in its path through the solar system. Understanding this object's orbital mechanics offers vital context to unravel its true nature and origins, setting the stage for worldwide scientific cooperation. Global scientific mobilization. As news of 3IATLAS's anomalies spread, the scientific community united in an unprecedented global effort to observe and analyze it. Major observatories around the world promptly cancelled all other planned projects to refocus on this singular target. This rapid consensus highlights the extraordinary importance scientists ascribe to an object that could reshape our understanding of interstellar phenomena. Among the most impressive shifts was the sudden repurposing of flagship space telescopes. The Hubble Space Telescope, renowned for its meticulous long-term scheduling, abruptly cleared its calendar to prioritize 3IATLAS observations. Similarly, the James Webb Space Telescope, whose precious observing hours are fiercely contested, granted the object top priority, signaling the urgency and weight of this mission. These decisions inevitably disappointed planned studies of distant galaxies and exoplanets, but underscore the unprecedented nature of this pursuit. On Earth, a global relay of ground-based telescopes formed a continuous observational network. Facilities in Hawaii smoothly handed off tracking duties to counterparts in Chile and beyond as Earth rotated, keeping 3IATLAS under near-constant watch. This collaboration ensures that no window of opportunity slips by unobserved and exemplifies international cooperation beyond typical scientific rivalry. Adding a unique vantage point, the SOHO spacecraft, typically dedicated to solar observation, was redirected to monitor the object as it approached the Sun. Though not designed for comet tracking, SOHO's position allows it to capture behavior impossible to observe from the ground, providing invaluable data on how 3I/ATLAS interacts with solar radiation and particles. Engineers had to develop new software to equip SOHO for this task, demonstrating the lengths taken to adapt existing assets to the challenge. Even more impressively, 2 European spacecraft orbiting Mars, Mars Express, and the ExoMars Trace gas orbiter are preparing to capture images during the object's close pass in October. Built to study Martian climate and geology, these craft were never intended for rapid interstellar visitor tracking. Their adaptation to this unexpected role highlights the extraordinary global commitment to this investigation. The depth of coordination across agencies, telescopes, and continents is staggering. Real-time data sharing, synchronized observations, and joint analyses have created a level of teamwork rarely seen in astronomy. The shared goal of unlocking 3IATLAS's secrets transcends typical nationalistic or institutional divides, forging a united front in cosmic discovery. This worldwide scientific mobilization underscores that 3IATLAS is no ordinary object, but a phenomenon commanding immediate, concentrated scrutiny. It has become the centerpiece of cutting-edge research, promising insights that could challenge fundamental astrophysical principles. With the global network in place and observations flowing, all eyes now turn toward a critical upcoming event that may decide the object's fate and reveal its deepest mysteries. As the world watches intently, scientists prepare to confront what could be the pivotal moment in understanding 3IATLAS's nature: the October perihelion passage, the October test. October 2025 marks a critical juncture in the unfolding story of 3IATLAS. This is when the object will make its closest approach to the Sun at perihelion. enduring the intense solar radiation that could reveal hidden details or cause dramatic changes. Scientists worldwide are preparing for this moment with both anticipation and caution, as it may answer fundamental questions or bring new ones. The Sun's fiery environment is the ultimate stress test for the object's icy exterior and internal structure. Before the perihelion encounter, 3I-ATLAS will pass near Mars, providing a rare opportunity for direct imaging by orbiters like Mars Express and the ExoMars Trace Gas Orbiter. These spacecraft will attempt to photograph the fast-moving visitor despite not being designed for such tasks. Capturing clear images at such speed and distance is akin to photographing a speeding motorcycle from another moving vehicle, underscoring the technical challenges involved. Success here could offer unprecedented insights into the object's surface and behavior. The approach to perihelion has already seen unexpected fluctuations in brightness and activity, suggesting internal processes that defy conventional comet physics. The Sun's radiation might trigger further outbursts or alterations in the coma, revealing details about its composition and potential internal heat sources. Alternatively, the object could begin to fragment or even break apart completely, as some comets do when exposed to intense solar heating. Either outcome will yield crucial information on its nature and origin. After perihelion, however, 3I-ATLAS will disappear behind the Sun for several weeks, blocking all direct observation from Earth. This blackout period will leave scientists in suspense, unsure whether the object remains intact, has fragmented, or transformed in unforeseen ways. It's a frustrating but unavoidable gap, akin to performing delicate surgery and then waiting anxiously to see if the patient recovers. The world will watch and wait until December, when observations can resume. Astronomers are developing innovative observation techniques to continue tracking the object as it moves closer to the Sun, despite the overwhelming glare. Observations during dawn and dusk may capture fleeting glimpses of 3I-ATLAS, akin to spotting a candle flame in the glare of a searchlight. These efforts push the limits of current technology and highlight the determination to not lose sight of this enigmatic visitor during its most vulnerable phase. What happens in October could have vast implications beyond this single object. If 3I-ATLAS withstands perihelion and reveals new physical or chemical properties, it may force a re-examination of comet formation and interstellar material. If it breaks apart or vanishes, scientists will gain insight into the limits of such bodies and their resilience. Either way, the outcomes will advance our understanding of cosmic phenomena and may influence future interstellar object studies. This perihelion also serves as a focal point in the broader question of intentionality. The object's precise trajectory and timing raise the question of whether some form of intelligence or natural design guided its arrival. Observations during this intense solar encounter may reveal traits consistent with either deliberate engineering or purely natural origins, helping to settle debates fueled by the object's earlier mysteries. Ultimately, October 2025 represents both a scientific challenge and a moment of profound discovery. The convergence of advanced technology, global collaboration, and cosmic timing sets the stage for revelations that could reshape our place in the universe. The world waits for what 3I-ATLAS will reveal next. 3I-ATLAS is challenging what we know about physics, chemistry, and interstellar travel, with each new discovery reshaping our view of the cosmos. Its improbable path and enigmatic behavior suggest this could be the most significant celestial visitor humanity has ever observed. Stay with us as this story unfolds. Like, subscribe, and turn on notifications to witness every step of this extraordinary journey.